Good morning, dear students. Today we will discuss Maxwell's electromagnetic equation which leads to electromagnetic wave equations. All of you know what is electromagnetic wave. We know electromagnetic waves are the wave which transmit energy from one point to another. The basic component of electromagnetic wave is electric field vector and magnetic field vector. And the electromagnetic wave plays an important role in communication, which enables us to transmit information wirelessly using various frequencies across uh, entire electromagnetic spectrum. And today we will see how mathematically we can see electromagnetic wave is a wave. That means it can show the wave characteristics mathematically. Before Maxwell came to the picture in year 1813. Before Maxwell, there was no uh, evidence of existence of electromagnetic wave theoretically. Only people believe that electromagnetic waves are the waves. But when Maxwell established his electromagnetic equation, we are able to see mathematically electromagnetic waves are waves, and where electric component and magnetic component are mutually perpendicular to each other, that property is called the transverse nature of electromagnetic wave. Also, it has characteristics of conservation of energy. It follows the energy conservation rule as stated by pointing. That also we can see mathematically by using Maxwell's electromagnetic equation. Now here today we will discuss how the existence of electromagnetic wave theoretically is possible with the help of Maxwell's electromagnetic equation. The Max just will discuss briefly about the Maxwell equation and what are its different mathematical forms. Maxwell's equation is the first unification of physical laws. We before before Maxwell, there are four established laws in electrostatic and magnetism. These four laws are Gauss law of electrostatic, Gauss law of magnetism, Ampere's circuital law, and Biot-Savart's law, and also the Faraday's law of electromagnetic induction. So these are the laws which has been established uh, established laws of electricity and magnetism. What Maxwell has done, Maxwell has modified the existing form of laws mathematically to differential form without changing the concept of the laws. That means the laws will be remains invariant when he is transferred the integral form of existing law to differential form. So these four laws just I have written here mathematically what are the different form of Maxwell's equation. The first equation is your Gauss law in electrostatic, that is phi E. Phi E means net electric flux over a closed surface is equal to 1 by epsilon naught times total charge enclosed in the Gaussian surface. Second law or second electromagnetic equation which we got from Gauss law of magnetism, that is net magnetic flux over a closed surface is zero. All of you know this law implies there is no existence of magnetic monopoles, or you may call there is the existence of magnetic dipoles. This is the second electromagnetic equation. Third electromagnetic equation is obtained from Faraday's law of electromagnetic induction, which implies EMF induced in the circuit is equal to rate of change of magnetic flux. That is E is EMF induced equal to d phi by dt. This phi is your magnetic flux. This negative sign arises due to the Lenz's law. What is that? The negative sign indicates EMF will be induced in opposite direction of the change of magnetic flux. So this is the Ampere circuital law. In line integration of B dot dl equal to mu naught I. So these are the four laws which already we know it. And how Maxwell changed this integral form to integral form to differential form by using two existing theorems, that is Gauss divergence theorem and Stokes theorem. What is Gauss divergence theorem? Volume integration of divergence of a vector over a closed surface is equal to surface integration of the same vector over the given surface enclosed within the volume. Then this is your Stokes theorem. Stokes theorem represents surface integration of curl of any vector field over a given surface is equal to line integral of same vector along the boundary of the closed path. So using these four laws, Maxwell has changed the existing integral form to differential form. So these are del dot E equal to rho by epsilon naught, del dot B equal to 0, del cross E equal to minus del B by del T, del cross B equal to mu naught Z. So these are the four differential form of the Maxwell's electromagnetic equation which we obtained by changing the existing integral form of the laws to differential form using these transformation theorems. Now we will see how these four equations will lead to electromagnetic wave equation. Electromagnetic wave equation we can obtain in different medium, in space, in free space or vacuum, in non-conducting medium as well as conducting medium. Here we will discuss electromagnetic wave propagation in free space or vacuum. Here you see volume charge density or charge density you can call in free space is 0 and current density also 0. And though it is free space, we will take mu as mu naught. Mu is what? Magnetic permeability. We will take here mu naught, which represents magnetic permeability in free space. And we will take epsilon naught as for electric permittivity, electric permeability in free space, epsilon naught. And what we'll do here, we will take the curl of Maxwell's equation 3 and 4 which we have written in previous slide, that is del cross E plus del B by del T equal to 0. If you take the curl of the vector, curl of the Maxwell's electromagnetic third electromagnetic wave equation, we will get del square E minus mu naught epsilon naught del square E by del T square. Similarly, if we take the curl of equation number 4, that is fourth electromagnetic equation, we will get the equation in the form of magnetic field vector. And these two equations what we obtained in terms of electric field vector and magnetic field vector, that is resembles the classical wave equation which is del square y by del x square equal to 1 by v square del square y by del t square. Though these two wave equations are similar to your classical wave equation, we may call these are the two wave equations in terms of electric component as well as magnetic component. So these two equations represents electromagnetic wave equation in free space in terms of electric field vector and magnetic field vector. If we compare these two equations with the classical wave equation, you will get the speed of the electromagnetic wave in free space is 3 into 10 to the power 8 meter per second, which we know the speed of light. So what we conclude here or what we get here, In free space, the wave which moves, electromagnetic wave which moves, has the wave characteristics and it moves with the velocity of speed of light in free space or vacuum. Similarly, in the same way, we can find the electromagnetic wave equation in conducting and non-conducting medium. Okay, thank you.